Hello everyone. In this lesson, we're going to be talking about our basic differentiation formulas. So if you watched my previous lesson, you'll remember that we did a fairly long limit where I showed you as you took the first, second, third, and fourth derivative, how it took a lot of steps, there was a lot to it, and now we're going to find some rules or differentiation formulas which will make doing differentiation a lot easier. So our first differentiation rule is that if we have the derivative of a constant, that is to say, if we take some derivative, d dx, so derivative with respect to x, of some constant c, the derivative will always be 0. Because remember, a derivative is a rate of change. A constant is not changing, right? So for example, if I had that f of x equals 4, and you say, okay, well, how much is it changing? Well, it's not. It's always going to be 4. So the derivative of a constant is equal to 0. The next is our power rule. The power rule is that if we have some d dx of some function x to the nth power, the way that we can solve this one is it's going to end up being n times x to the n minus 1 power. Meaning, if, for example, if I take the derivative of x to the 4th power, I would bring the 4 down, so this becomes 4x to the n minus 1, or 4 minus 1, or 3rd power. So it'd be 4x to the 3rd power. Our third rule is the constant multiple rule, which is if we have d dx and we have some constant times our function f of x, this will be the same thing as taking the constant times the derivative with respect to x of our function f of x. So what does this mean? Well, it means something like, for example, if I have 3x to the 4th, like we were just looking at, x to the 4th, this would be the same thing as if I took the derivative of x to the 4th times 3, or whatever number it was that I said. So you could actually pull that constant out, take the derivative of the function, and then multiply that by the constant, and you'll get the same derivative. Okay, so now we have the sum and difference rules, which is to say, if I have the derivative d dx of two functions, f of x and g of x, so plus or minus g of x, this is going to be equal to the derivative of f of x plus or minus the derivative of g of x. And this is just like when we did limits. If I had the limit of some function f of x plus or minus g of x, I could take the limit of f of x plus or minus the limit of g of x. This still holds true for derivatives. So if I have the derivative of f of x plus or minus g of x, this will be the same thing as the derivative of f of x plus or minus the derivative of g of x. Our next rule is whenever we take the derivative of a natural exponential function, that is to say d dx of e to the x, this is just going to be equal to e to the x. So this is actually one of the easier functions to do. Now later on we will learn more about this when you have something that's more complex within the power. For example, this will be using something called the chain rule, which we'll talk about later. But for now, if you have e to the x, take the derivative of it, and you're just going to get out e to the x. And then a couple more for some trig functions. If we have the derivative d dx of sine of x, this is going to be equal to cosine of x. And if we have the derivative d dx of cosine of x, this is going to be equal to negative sine of x. So these are some of our basic building blocks we're going to be using as we start building out our derivative rules that we can use. So these are always going to be useful, right? If you ever have a derivative of a constant, it's always equal to 0. The power rule, that's what we're going to be focusing on mostly in this section. If you have a constant times some function, you can take the derivative of the function, then multiply it by the constant. If you have the derivative of two functions added or subtracted, you can take the derivative of the first, added or subtracted to the derivative of the second. If you have the derivative of the e to the x function, then you'll just get out e to the x. If you have the derivative of sine of x, you'll get out positive cosine x. If you take the derivative of cosine x, you'll get out negative sine x. And then, of course, you can actually kind of go back and forth with this. So if I took the derivative of that negative sine x, sine x, right, you could think of this multiplying by negative 1. This would become cosine x times negative 1, or negative cosine x. If I did the derivative of negative cosine x, I would get negative sine x, which would be positive sine x. And basically, it's just going to cycle through them every 4. So let's look at some quick examples. Let's say that we have, by the way, I'm going to leave these rules here as we work through the problem, so you always have them to reference while we're looking at this. Let's say that we have the function f of x is equal to e to the x minus x. And we want to take the derivative, the second derivative, and the third derivative. So using our definition of a derivative, what we would have had to do is we would have had to take the limit as h goes to 0, f of x plus h minus f of x divided by 0. So we'd have to divided by h. We would have had to plug in x, this would be our f of x. We would have had to plug in x plus h in each of these. We would have had to then solve for this, get rid of the h in the denominator, solve for as h goes to 0, and you would get your first derivative. Then you'd have to do the same thing for the second, same thing for the third, any derivative you want to do. But what we're going to do now is we're going to be using our rules. So we have f prime of x, which we're going to be looking at the fact that we have the derivative of e to the x minus x, which using this rule right here, we have e to the x, we have x, and they're subtracted from each other. So this is going to be the same thing as taking the derivative d dx of e to the x minus d dx x. Now, again, using our rules, what is the derivative d dx of e to the x? Well, according to rule 5, this is just going to be e to the x. Okay, what would be the derivative of, what would be the derivative of x? Well, you could think of this x as x to the 1. Using our power rule, if I have x to the 1, I bring down the 1, and then I have x to the n minus 1. Well, n in this case is 1, so if I have x to the 1 minus 1, this is the same thing as saying I have x to the 0. So this would be e to the x minus 1 x to the 0. Anything to the 0 power is just equal to 1, so this ends up being e to the x minus 1. So the next thing we're going to do, we're going to take our second derivative. So this is going to be f double prime of x. So we're going to take the derivative of this function. So this is going to be d dx e to the x. And we're going to split it because we have minus some other function. In this case, it's 1. So this is going to be d dx 1. Again, looking at our rules, derivative of ex, e to the x, is going to be equal to e to the x minus derivative of a constant, 1 is a constant, is equal to 0. So e to the x minus 0 gives me e to the x. And then if I take my third derivative, I'm going to take d dx of e to the x, which is just going to be e to the x. And just like we talked about previously, what happened with my original function as I took the derivative? Well, e to the x doesn't change, but I went from x to the 1 to x to the 0 to a constant that then just goes to 0. So each time it got less complex as I took the derivatives. So now what we're going to do is we're going to take some functions and use the power rule to solve for them. So our first function is going to be f of x is equal to x to the 6th power. So using our power rule, what's going to happen is we're going to pull, so we take the derivative, we're going to pull that 6 down. So we're going to get 6 x to the n minus 1, or 6 minus 1, which is going to be 6x to the 5th power. If we had y is equal to x to the 1000 power, using 1000, we're going to use the same rule. What's going to happen is that we're going to pull out 1000. This is going to be x to the n minus 1, so 1000 minus 1 would be x to the 999th power. If we had g of x is equal to 7, when we take the derivative of this, so we have g prime of x, this is going to be the same thing as saying 7x to the 0. So what I would need to do now is I would pull this first term down, right? So I pull my n down. In this case, it's going to be, actually real quick, if you want to be technical, we're actually using this one first. Constant times a function. If we take the derivative of that is the constant. So this is actually going to be 7 d dx x to the 0. So now let's do that. So we have 7 times, if I have a 0 in power, I'm going to bring that down, 0, x to the negative 1. Well, anything times 0 is going to be what? 0, and then 0 times 7 is also going to be 0. Our next function h of x is going to be 3x to the fourth power. So again, we're going to, if you wanted to kind of follow all these rules, generally we just do it all in one step, but just to be precise, this is the same thing as taking 3 times d dx x to the fourth. So I'm going to bring that 4 down, so this is going to be equal to 3 times 4 x to the 4 minus 1, or third power. This is going to give me 12x cubed. My next function, f of x, is going to be equal to 1 over x squared. So this one is a little bit more complicated because we have to actually put it in terms of a power. So if I have 1 over x squared, remember, a negative power will take something from, if you have it up in the numerator, it'll bring it down to the denominator as a positive. If you have something in the denominator that is positive, it's the same thing as saying that I have x to the negative 2. Taking our power rule, my power is negative 2. So I'm going to pull that negative 2 down. So it'd be minus 2x, and then n minus 1. Negative 2 minus 1 gives me negative 3. And then if I wanted to write it back in its original form, this would just be equal to negative 2 divided by x cubed. And then the last one we'll look at for now is going to be if we have hx is equal to the cube root of x squared. So as before, when we have some power that's in the denominator, you could switch it by making it a negative power. The root function is a fractional power. So this would be x squared to the 1/3, or x to the 2/3 power. So we have x to the 2/3 power. We're going to use the same rule though. We're going to bring down our n, which in this case is 2/3. Oops. This is not true. This is h prime of x. So we're going to bring down our 2/3. So this is going to be 2/3 x to the n minus 1. So 2/3 minus 1. So 2/3 minus 3/3 is going to be negative 1/3. Now, if we wanted to write it back in sort of its original form, this is going to be equal to 2 over 3 x to the negative 1/3. Well, x to the 1/3 would make it a third root or cube root. The negative is going to bring it into the denominator. So this is going to be 2 over 3 times the cube root. Let me write that because I made it too small. This is going to be 2 over 3 cube root of x. For our next example, what we're going to do is we're going to find the tangent line and the normal line, which is the line that's perpendicular to the curve y equals x square root of x at the point 1, 1. Because we're going to need some specific point to find the tangent line, right? Because the derivative tells us the instantaneous rate of change at any given point. To find a tangent line, we have to know what point we're finding the tangent at, and then from there we can figure out what the normal line is to it so that it's perpendicular. So the first thing we're going to do is we have this function f of x is equal to x square root of x, which I'm going to rewrite in terms of a power so I can use my power rule. So this is going to be equaling f of x equals x times the square root of x is just going to be x to the 1/2. Now, if you watched our review or you just remember how to deal with powers, you can consider that x to the 1/2 times x, which is x to the 1, you just add those two powers together. So this would be x to the 1 plus 1/2, or x to the 3/2 power. So what we're going to do first now with this is we're going to take the derivative in order to figure out what is my instantaneous rate of change. So this is going to be d dx x to the 3/2. So using our power rule, we're going to bring down 3/2, x, and then this is going to be n, so 3/2 minus 1. Well, in this case, 1, because I want it to be in terms of halves, would be minus 2 over 2. So 3 over 2 minus 2 over 2 is going to leave me with 3/2 x to the 1/2 power. And then, of course, rewriting this in terms that we did when we had our original function, this would be the same thing as saying 3 square root of x over 2. Now what we want to do is we want to figure out where is our tangent line. This is our instantaneous rate of change. But we had a specific point, 1, 1. So if I plug in 1 for x, so f prime of 1, this is going to be 3 times the square root of 1 over 2, which is going to be, so square root of 1 is 1, so we have 3/2. So this is our slope of our line. And now what we're going to do is we're going to use our point slope form for our line, which is going to be y minus y1 equals m times x minus x1, and we're going to plug in 1 and 1 for y1 and x1. So this is going to be y minus 1 equals my slope of 3/2 x minus 1. We're going to distribute our 3/2, so this is going to go to y minus 1 equals 3/2 minus 3/2. I'm going to add 1 to both sides. Cancel. I'm going to get y equals, I forgot my x, 3/2 x, and then we have minus 3/2 plus 1. So just like before, I can make this 2 over 2. So I have 2 over 2 minus 3 over 2, which would be minus 1/2. So this is my tangent line. I have an intercept of negative 1/2. So let's say this is negative 1. I'm intercepting here, and I have a slope of 3 over 2. So it'll be 1, 2, 3, 1, 2, something like this. And now what I want to do is I want to figure out what is the line that is perpendicular to this at that point right there. So what I'm going to do in this case is I'm going to take my slope, which we had was 3/2, and I'm going to flip it and take the negative of it to get the slope of the normal line. So this is going to go to m equals negative 2 over 3, right? Because that's how we would get. So if this is 3 over 2, the slope of this would be negative, and it would be negative 2 over 3. So we have our slope, we have our same point, so then we're going to do the same thing. We're going to have y minus 1 equals negative 2/3 x minus 1, and we'll solve it exactly the same way. Y minus 1 equals negative 2 over 3x plus 2/3. We're going to add 1 to both sides. We're going to get y equals negative 2/3 x. And then so we have plus 2/3, and then this would be 3 over 3. So plus 3 over 3 would be plus 5/3. And this would be our normal line to our tangent line at the point 1, 1. So now that we've looked at some examples of using our power rule, let's look at some examples using our constant multiplication rule, which is this rule right here. So let's say that we had d dx 3x to the 4th power. So if I wanted to take the derivative of this, well, based on our constant times a function rule, what we can do is we can pull that 3 out. So this is going to be equal to 3 d dx x to the 4th power. So this will be 3 times 4x cubed, which is going to give me 12x cubed. If we wanted to take the derivative of the function negative x, you could think of this negative x as negative 1 times x. I can pull that negative 1 out, so this would end up being negative 1, or just negative, d dx x. If I take the derivative of x, which is x to the 1st power, I pull 1 down. 1 minus 1 for the power gives me a power of 0. This would be equal to negative 1. If I took the derivative, so d dx of negative 6 cosine of x, same idea. The derivative of a constant times some function, I can pull that constant out. So this will be equal to minus 6 d dx cosine of x. And then based on our limit rules, if we take the derivative of the cosine of x, this is going to be equal to negative 6 times negative sine of x. And we have a negative and a negative. This would give us 6 sine x. Let's look at a more complex function to kind of bring some of these rules all together. Suppose we have d dx of x to the 8th power plus 12x to the 5th power minus 4x to the 4th power plus 10x cubed minus 6x plus 5. So if we wanted to do this derivative, first thing I'm going to do is I'm going to split up my derivative into individual derivatives using our addition-subtraction rule. So this is going to be equal to the derivative, so d dx of x to the 8 plus 12, sorry, don't want to skip any steps, d dx 12x to the 5th minus d dx 4x to the 4th plus d dx 10x cubed minus d dx 6x plus d dx 5. I'm going to then focus on these terms that have constants in front of them. So I'll pull those out. So this is going to end up being d dx x to the 8th plus 12 d dx x to the 5th minus 4 d dx x to the 4th plus 10 d dx x cubed minus 6 d dx x plus d dx 5. And now let's solve. So we have x to the 8th power. So we're going to pull that 8 down. So there's going to be 8x to the 7th power. Plus, for derivative with respect to x of x to the 5th is going to be, we're going to pull that 5 down. It's going to be 5x to the 4th power. So 5 times 12 is going to give me 60 x to the 4th power minus derivative of x to the 4th. We're going to pull that 4 down. So this is going to be minus 16x, and then that 4th power goes down by 1, so cubed. Here we have plus 10. We're going to pull that 3 down. So this is going to be plus 30. X cubed becomes x squared minus 6. So x to the 1, we already talked about this. Derivative of x is just going to be equal to 1. So this is going to be minus 6. And then the derivative of a constant is going to be plus 0. So that term goes away. So we have 8x to the 7th plus 60x to the 4th minus 16x cubed plus 30x squared minus 6. And you can imagine plugging this into our definition of a derivative where we're taking the limit of f of x plus h minus f of x over h. This would be a lot more complicated to do because when we did the x plus h, we would have to take into account an 8th power, a 5th power, a 4th power, a 3rd power, and a x to the 1st power. That would be a really long function that we would have to then take the limit of. There'd be a lot of cancellation. You'd be able to do it, but this is so much simpler just using our derivative rules. Now for our next problem, we have y equals x to the 4th minus 6x squared plus 4. And we want to find where this function has a tangent line that is horizontal. So first things first, whenever we want to find a tangent line, we need to take the derivative. So we're going to get y prime is equal to, bring the 4 down, so it's going to be 4x cubed, minus, we're going to bring the 2 down, so it's going to be minus 12x, and this constant is going to go to 0. So we have 4x cubed minus 12x as our derivative. Well, the way that we find where the tangent is equal to 0 is basically what we're saying, remember, is that the rate of change is equal to 0, meaning wherever we have a tangent line that is horizontal. So this would be when it's equal to 0. So we need to set this equal to 0. So we have 4x cubed minus 12x equals 0. What I'm going to do now is each of these terms have an x in them, so I'm going to pull an x out. So we have x, 4x squared minus 12 is equal to 0. So first of all, I can get 0 by plugging in x equals 0. So now let's focus on this term here. Where is 4x squared minus 12 equal to 0? Well, as before, if I wanted to, I could pull a 4 out of this. So this is going to be 4x squared minus 3 is equal to 0. So divide each side by 4. 0 over 4 is 0. So we get x squared minus 3 is equal to 0, which would be x squared is equal to positive 3. So what does this mean? Well, this means then that my x's where I can have this equal to 0 would be x equals negative square root of 3 and x equals positive square root of 3. Because remember, whenever you have a square term, you have to consider that both the positive and the negative can make this true, right? Because if I took negative square root of 3 and I squared it, this would just end up being negative square root of 3 times negative square root of 3. Negative and negative makes it positive. Square root of 3 times square root of 3 just makes it equal to 3. So you have to consider that there's both the positive and the negative. So this means that this function would have a tangent line that is equal to 0 at x equals 0, x equals negative 3, and x equals negative square root of 3, and x equals square root of 3. If we were to plug these back into the original function, we could actually find out those points. So if I were to plug in x equals to 0, I would get 0 minus 0 plus 4. So I would get 0, 4 for the first point where I have a tangent line tangent that is equal to 0. For the second one, I'm going to plug in the square root of 3. So if I plug in the square root of 3, this becomes the square root of 3 to the fourth power should be 3 squared, which is going to be equal to 9 minus 6 times square root of 3 squared, which is going to be times 3, so minus 18, plus 4, which is going to give me negative 5. And then, of course, if I plugged in positive square root of 3, I would get the exact same value. So negative square root of 3 minus 5. So these are the 3 points where our tangent line would be equal to 0, or that is to say we have a horizontal tangent line. And later on, we'll talk more about this when we talk about maxima and minima. These would be the points where we either have a maximum, a minimum, or an inflection point. For our next example, let's say that we have a position function of a particle that is s is equal to 2t cubed, which t is time, minus 5t squared plus 3t plus 4, where s is going to be measured in centimeters and t is our measurement in seconds. We want to find the acceleration as a function of time and then find out what is the acceleration after 2 seconds. So the first things first is this s of t. This is our position of our particle based on some amount of time. So we have st is equal to 2t cubed minus 5t squared plus 3t plus 4. So we're going to find our derivative to figure out what is the velocity of our particle. So this is going to end up being 6t squared minus 10t plus 3. This would be the velocity. But the question asks us for the acceleration, meaning we want to take the second derivative of our position with respect to time. So this is going to become 12t minus 10. Now that we have our second derivative, which tells us the acceleration, if we wanted to know what is the acceleration after 2 seconds, we would just plug 2 into this. We would get 12 times 2 minus 10, which is going to be equal to 24 minus 10, or 14 centimeters per second squared. The next question we want to look at is, at what point is the curve y equals e to the x, at what point is the tangent line parallel to the line y equals 2x? So what does it mean that if the tangent lines are parallel? It means that the derivative of this, which is of course going to be e to the x, is going to be equal to the derivative of this, which is going to be equal to 2. So pretty much what we're saying is, when is e to the x equal to 2? So we'll set it up with e to the x equals 2, and we want to solve for what x makes this true. So to deal with this e to the x term, what we're going to do is we're going to take the natural log of both sides. So natural log of e to the x equals the natural log of 2. The natural log and the e cancel, and you will get x is equal to the natural log of 2. So this would be the x value for the point for when y equals e to the x is parallel to y equals 2x. So now what we need to do is we need to plug in that natural log of 2 into our original function, which it should be either function, because remember we're saying they're equal here. that means that if we plug that into our original function, we would get natural log of 2 e to the natural log of 2, right? So we have e to the natural log of 2. Again, these two would cancel. You'll just be left with 2. So the point where these two, the tangent lines are parallel to each other, would be natural log of 2, 2. So this would be our x value, and this is our y value. If we have the function y equals 3 sine of theta plus 4 cosine of theta, what would be the derivative for this function? So first things first, let's do y prime is equal to d dx 3 sine of theta plus d dx 4 cosine of theta. And we're going to use our constant rule to pull the 3 and the 4 out. So this is going to be 3 d dx sine of theta plus 4 d dx cosine of theta. Now, using our derivative rules, the derivative of sine of x is equal to cosine x. So this is going to be in this case, theta, would be 3 cosine theta plus 4, and then the derivative of cosine is going to be minus sine. So this means that we're having negative sine of theta. What about if we had the function f of x is equal to cosine of x, and we wanted to figure out what is the 27th derivative of, the 27th derivative of this function? Well, what we're going to do is first we'll take the first derivative. So we have f prime of x, and this is going to be equal to negative sine x. So we have negative sine x. We'll take the second derivative. So we'll take the derivative of negative sine x, which would be negative cosine x. We'll take the third derivative of x. So we take the negative derivative of cosine x is negative sine x. Negative negative will give us sine of x. And then we'll take the fourth derivative of x, and this is going to give us cosine of x. So now we're back at the beginning. So pretty much what's happening is every 4 derivatives, we are going back and forth from cosine x, negative sine x, to negative cosine x, to positive sine x, to positive cosine x. So if we were to repeat this, we basically are going to say, okay, well, if we want to take 27 and we want to figure out how many times we can divide this by 4, so we're going to look at how many ways can 4 go into 27, which is going to be 6. So 6 times 4 is going to be 24, which would give us a remainder of 3, meaning that it is going to be equivalent to the third derivative. So f27 is equivalent to the third derivative of f of x, which in this case would be sine of x. So the 27th derivative of cosine x would be sine of x. Now, the last thing I want to do in this lesson is I want to go back to our function that we looked at in the prior section. So we had f of x was equal to x cubed minus x. And what we did is we found the derivative, we found the second derivative, we found the third derivative, and we found the fourth derivative. So I just want to quickly show how fast we can do this now and to make sure that it fits with what we got previously. So when I take the first derivative, so f prime of x, I am taking the derivative, so technically I'm taking the derivative of x cubed minus x, which is equal to the derivative, so d dx x cubed minus d dx x. Well, using our power rule, this is going to be 3x squared, and this d dx x is just going to be equal to 1, so minus 1. So that matches what we got. Now we're going to take the second derivative. And this is going to be equal to, I'm going to bring down to 2, so it's going to be 6x. 2 minus 1 is going to be 1. This 1 is going to go to 0, 6x. Now I'm going to take the third derivative. So this is going to be d dx 6x. I'm going to pull that constant out. This is going to be equal to 6 d dx x. We just talked about the fact this is going to be equal to 1. So this is going to be 6. And then for my fourth derivative, we are taking the derivative of 6, which the derivative of a constant is always equal to 0. So if you look at these terms, we got the exact same thing. And you see how much faster it is using this power rule. And in fact, and also the constant rule and stuff like that. But in fact, I'm writing down more steps than you really need to even solve this, right? If I have x cubed minus x, I just need to pull out 3, so 3x squared minus 1. Next one, I have the derivative of 3x squared minus 1. That becomes 6x, and then the other term goes away. Take the derivative of 6x. I know x to the 1 is just going to be equal to 0 when I take the derivative, so it's going to be, equal to 1 when I take the derivative, so it can be 6, and then derivative of constant is 0. So we went from basically a full board of calculations to figure out these 4 answers, or we could pretty much do it in our head, and it takes seconds. And this is sort of the power of these derivative rules that we're using. Now remember, even though we're using these rules and we're very quickly figuring out the derivative of some power or constant times a function, things like that, but what you're fundamentally doing underneath the hood is you're using that definition of a derivative that we talked about earlier. The difference is, though, now is we're not showing all the individual steps because this has been rigorously proven to be true. So we're basically using a shortcut now to solve these very quickly. Thank you for watching. To continue learning, click the linked video here for the next lesson. If there's a topic you'd like me to cover, let me know in the comments. Don't forget to subscribe, and I'll see you in the next video.